다들 즐거운 점심 식사 시간 되셨길
Enjoy your
바라겠습니다.
lunch.
바로 이어서 오후
Then we would
세션을
like to,
진행하도록
without further
하겠습니다.
ado,
세 번째
begin
세션을 이어가
session
보겠는데요.
3.
AI 빅데이터 기반
The session 3
우주전파
is
환경이라는
about the
주제로
space weather
문준철
based on
연구자님께서
AI and
가장을
big data.
맡아 세션을
And
이끌어 주시겠습니다.
Dr. Moon Jun-chul will
부장님께
serve as
진행을
a moderator.
부탁드리겠습니다.
I would like to ask Moon to go ahead and proceed.
네, 안녕하십니까.
Good afternoon. I will serve as a moderator for session 3. My name is Moon Jun-chul.
세션 3는
And in this session 3,
분의 연사분께서
we have 3 speakers.
발표자들은
And each speaker will have 20 minutes for presentation and 5 minutes for Q&A.
질의응답은 사전 질문과
As for the Q&A, we will open up the floor, and we also have several selected questions as well.
그럼 먼저 세션
First of all,
첫 번째 과제인
the first presentation
AI 기술을 활용한 우주전파
is about
예보에
the
대해서
space weather prediction based on AI. And Dr. Bing-Xian Liu will make a presentation. Do we have him here?
본 발표는 사정상 사전 영상으로
Due to
Let's
he
get
will
you
make
started.
a
Okay.
presentation
Let's
in
get you started.
video.
Thanks for coming. As you know, artificial intelligence, or you can call it machine learning, finds its way in space weather prediction services. I'm very glad to give a presentation today to talk about our recent applications of artificial intelligence at our Space Weather Forecast Center. We are affiliated with National Space Science Center, Chinese Academy of Sciences. We have established a national team to develop AI applications for space weather services. The team members are from several universities and institutes across the country. Later on, I'm going to briefly explain 3 AI applications that we are currently using. 2 of them are for flare predictions, and there's one for CME arrival forecasts. This slide shows you a list of personnel together with their affiliations. Some of them you may already know. They are part of the national team. To pursue our objectives, the team should consist of not only researchers and scientists with specialties in solar physics or space weather services, but also AI and computer vision experts. This is a quite active team. We have hosted a series of seminars. We provide a joint supervision for graduate students. We have sponsored 2 challenge events. Of course, we have research collaboration among team members. Teamwork is very important. All the achievements I show in this slide come from collaboration. In 2021, we sponsored an artificial intelligence challenge over solar storm recognition and prediction. For the challenge, we set up 2 subjects. One is sunspots recognition, and the other is solar flare prediction. 66% of the participants were from universities, while 10% were from research institutes. We also had attendees from companies and other agencies. This photo here was taken after the award ceremony. We sponsored another challenge in 2022. This challenge is about geomagnetic storm prediction. The participants were required to use AI algorithm to predict the KP index. The winner of the competition is from Central South University. International collaboration is necessary. Supported by the Beijing branch of International Space Science Institute, we interact with international scholars and mutually benefit each other. The first AI application I'm going to share with you today is the knowledge-informed modeling for flare prediction. In fact, forecasting flares is one of the major topics in space weather services. Machine learning can give quite nice results under some circumstances. However, human is not a race to be satisfied easily. We notice that prior knowledge is useful. We believe that the physical characteristics can play a role. These properties include areas of active regions and magnetic types and so on. Therefore, we would like to combine the prior knowledge with a machine learning algorithm. This is the so-called knowledge-informed modeling. We have published our experiments in space weather. I show you two tables in this slide. One is the relationship between magnetic type and the flare productivity in the next 48 hours. And the other is the relationship between active region area and the flare productivity in the next 48 hours. Evidently, the simple alpha type produces very few M-class flares in the next 48 hours. So does the active region with a very small area. These two tables are nothing but the prior knowledge. We can summarize the prior knowledge and conclude to several factors. First of all, magnetic type and area are highly related to flare productivity. Second, active regions with simple magnetic type hardly produce large flares. Third, active regions with a smaller area have lower flare productivity. We use the prior knowledge to guide the model training process. The guidance lives through data processing, sample grouping, and the implement of extra parameters. We use the photospheric magnetic field image to train our AI model. We need to do data processing before model training. We fill the original rectangle image to a square image. Then we resize the image to a smaller size of 160 by 160 pixels. Then the images are ready to be used. The CNN model we have used consists of convolution, pooling, and fully connected layers. Of course, a pure CNN model can be used to forecast strong flares in the next 48 hours. But we're not going to construct a pure CNN model. Instead, we build knowledge-informed AI model. We use prior knowledge to do sample grouping first. We group the data samples into two subsets according to different flare productivities. Subset 1 has two conditions. One is that the magnetic type is alpha. The second one is that the active region area is less than 100. Then we put the rest into subset 2. We have built two knowledge-informed models. We name them Fusion Model 1 and Model 2. I'll talk the Fusion Model 1 first. Fusion Model 1 is of two submodels. Submodel 1 is quite simple. It just classifies subset of 1 as 0. The submodel 2 is a CNN model. This figure here vividly illustrates the workflow of Fusion Model 1. Alright, let's talk about Fusion Model 2. The red arrow in the figure implies that we are using active region area as an extra input parameter. Active region area is one kind of the prior knowledge. It is very natural that we use active region area as an extra input. This is just one step further from Fusion Model 1. We compare the performance of a pure CNN model to our knowledge-informed model. Indeed, all the three models are constructed to forecast strong flares in the next 48 hours. The table shows the detail. You can find F1 scores for all the models here. We'll just read them out. Pure CNN 0.245, Fusion Model 1 0.272, Fusion Model 2 0.385. The bottom is the true scale. I'll also read them out. Pure CNN 0.587, Fusion Model 1 0.564, Fusion Model 2 0.695. The result proves that the knowledge-informed prediction models perform better than the pure CNN model, and the Fusion Model 2 performs even better. Such a result is expected since the active region area is one of the very important factors. You can find more details in Lee et al. 2022. We can use artificial intelligence over anomaly detection. Although the physical mechanism of solar flares remains a puzzle, we are still trying very hard to develop prediction tools for solar flares. In fact, there's a lot of work laid ahead. For example, how to increase the prediction accuracy, or to provide a larger prediction window. It is very hard, but we still have a clue. It is noticeable that stable active regions are related to non-strong flaring, and the abnormal evolution of active region are always related to strong flaring. Such a situation inspires us to detect abnormal evolution of solar flares using anomaly detection algorithm. As usual, the first step is to prepare datasets. What we use is the radiomagnetic field of a sharp patch. First, we randomly cut the image into multiple squared slices. Then we resize the slices into smaller size. This is a very common procedure. The picture here is a demo. We use autoencoder network to detect anomaly. In other words, we consider the non-strong flaring active regions as normal, and we consider the strong flaring active regions as abnormal. Now here, I will use the active region 11192 to show you how the anomaly detection works. The left-hand side is the sharp patch. First, we randomly cut 10 slices out of the image. Then we resize them into 32 by 32. The slices are indexed from 1 to 10. The first and the third rows are the original slices of 32 by 32. The second and the fourth are reconstructed by the autoencoder network. For stable active regions, the autoencoder network can produce a picture similar to the original one. Then the mean square error between the original and the reconstructed pictures can be used to detect abnormal features of active regions. We can consider the abnormal features to be the precursor of strong flares. The chart here shows you how it works. Indeed, the number of slices is not limited to 10. Suppose we have slices of a number n. Each slice is a picture of 32 by 32 pixels. The autoencoder network is an unsupervised neural network. The slices go to the autoencoder network. They come out the reconstructed pictures of the same size. Then we can compute the MSE. The result goes into a strong flare classification model. We can set up a threshold for the MSEs. If none of them exceed the threshold, we think it's all normal. Then a negative forecast is given. If some MSEs exceed the threshold, then we think it's anomaly. Consequently, we give a positive forecast. That is, it may be an active region with strong flares. The top panel shows the dependence of the performance of the model on the MSE threshold. Bottom is the dependence of warning time on the MSE threshold. The model reaches an F1 score of about 0.8 and an average first warning time of about 45 hours for the same threshold. The magnetic structure precursor of active regions appears sometime before the strong flare eruption, and the obtained average maximum warning period for strong flare prediction is nearly 2 days. And this might be useful for future applications for space weather, solar flare prediction. More details can be found in Wang et al. 2022. The last artificial intelligence applications I'm going to talk today is for CME arrival forecast. Well, now I would like to clarify that this application is not for the prediction of CME eruption. In fact, there are two machine learning models. One is for the CME arrival prediction. Another is for CME arrival time prediction. The paper published in 2021 developed a model for the arrival time of CME. It uses recommendation algorithm with the combining of multiple data to predict the arrival time. The paper published in 2022, combining recommendation algorithm and the logistic regression method, to develop a model to predict whether or not a CME will arrive at the Earth. This slide gives you an overview of all the data we have gathered. We have the CME parameters. We have CPA, MPA, angular width, linear velocity, etc. We gathered the CME source information. If a CME is associated with a flare, it is assigned the active region number. If a CME is associated with a filament, we use the center of the filament as the CME's location. We include the following parameters in our model, as well as the radiation flux F10.7. Totally, there are 18 parameters in our model. The total number of the CME events in our model is 215. We use 156 events as the training set. The number of the validation sets is 39. 20 events are used as the test set. Here, we list all the parameters we used in our model. All the data go into the CME recommendation system. We can use cosine distance or the Euclidean distance to calculate the similarity. The recommendation system matches the most similar historical event from the CME library based on the input data. And finally, a historical similar CME event is selected as a reference to predict the arrival time of the CME. This slide shows you the model performance. Evidently, the performance of the Euclidean distance is better than the cosine distance. The mean absolute error, standard deviation, root mean square error of the Euclidean distance are all better than the cosine distance. We also compared our model performance to the CME scoreboard. For the 31 events, we plotted together the errors from different models together for comparison. The plot shows our model when taking the Euclidean distance is slightly better than the average, and the cosine distance is slightly worse. You can find more details in Shi et al. 2021. This slide shows you the recommendation model to predict whether or not a CME will arrive at the Earth. The model combines the recommendation algorithm and the logistic regression method. The idea of this model is quite simple. We would like to select a historical CME event as a reference to predict whether or not a CME will arrive at the Earth. There are 3,667 events in our dataset. Each event has 18 parameters. We introduce the weight training process. 1,833 events are included in the weight training process. 1,466 events are in the training set. 367 events are in the validation set. We adopt both logistic regression method and the recommendation algorithm in the weight training process. For the logistic regression, we use two different types of methods. For each method, we use the original data and the oversampled data. For the recommendation algorithm, we use both the cosine distance and the Euclidean distance. So there are totally 6 different training processes. We evaluated them and determined a combination of the optimal weight. The recommendation test procedure has 1,833 and 34 events. We use 3 different types of methods to do the recommendation test. One is the logistic regression with a weight directly from the logistic regression training process. Another one is the recommendation algorithm with a weight directly from the recommendation algorithm from the weight training process. What we expected the most is the method using the combined optimal weight. I will show you the results on the next slide. The table on this slide gives you an impression of the performance of our model. The red box highlights the best test with an accuracy of 88%. I guess I will stop here and thank you again for listening.
네, 감사합니다.
Thank you very much.
혹시 질문이 있으시면
If you have any question, please let us know, and we will compile all the questions and deliver this question to the presenter. Is there any question?
네, 없으시면
If not, we would like to move on to the next presentation.
다음 발표는 제가 발표드리는데요.
I'm the next speaker,
잠시 자리를 옮겨서 발표드리도록
so I'd
하겠습니다.
like to move to the podium to make a presentation.
네, 안녕하십니까. 제가 발표드릴 내용은 디지털 기반 우주전파환경 통합정보 시스템
The topic of my
개발입니다.
presentation is the development of the integrated information system, which is a digital system for space weather forecasting. I would like to talk about the current pain points, and then I'll talk about the establishment of the cloud and AI big data-based infrastructure, and we'll conclude my presentations with some of the points related to the model integration. We developed the forecast and warning system in 2011, and we've been using the system for more than 10 years. And the system has been aging, and that has caused some problems. So now we understand that there is a need to develop a new digital information system. And another problem is that since the forecasters analyzed the monitoring data using their own insight and subjectivity, and because of the lack of the subject data, there are some differences between the outcomes that are produced by forecasters.
원인이 됐었습니다. 그래서 이러한 점을 개선하기 위해서는
So in order to solve the issues, we need to secure more objective data using AI and big data,
세 번째로
so that we can use the data analysis outcomes for our forecasting and warning.
AI 빅데이터 기술뿐만 아니고
We can use AI and big data technologies, and we also need to use other statistics-related techniques in order to process a large amount of data.
이게 분석을 하기 위해서는 이제 프로그래밍 언어가 좀 필요한데 그런 것들도 좀
And we also need to understand the programming languages in order to be able to better analyze the data.
저희 내부뿐만이 아니고 대국민 대상으로도 쉽게 데이터를
And also in order to better inform the general public about what's happening in space weather, we need to have better and quality data and need AI-based analytics. That's why we developed integrated information system, And the development period was for 2 years from 2020 to 2021, and the budget was 12.1 billion Korean won. In the first phase of the project, we worked on developing the hardware, and in the second phase of the project, we developed applied systems. Those are 6 business websites. So you see number 1 to 6, and these are all different components of the information system. So we have forecasting and warning system, and there is also below the AI and big data system. We have disaster response system and integrated control system, knowledge sharing, and external service. There is a difference between the current one and the previous one. We used to have only the website or the system for the forecast and the warning system. And for the remaining 5 businesses, we had to develop the new systems. And when it comes to the model integration, all the models run individually on different endpoints, like the PCs.
한 군데서 제공하는 게 아니고 다양한 똑같은 데이터인데도 다양한
with the same data,
한 루트를 통해서 받아오는 그런 상황이었어요. 그래서 되게 복잡한
those data
그런 환경이다
was
보니까
called in
모델
using
활용에
different routes,
어려움이 있었어요.
and that had caused some difficulties utilizing the models. So we identified all the existing issues and wanted to bring together all the data source in one place, and we wanted to bring that data source through the same channel for our analysis.
AI 인프라 구축입니다.
So the first phase of our project was to establish the cloud and AI big data infrastructure, and there is the external network and the internal network. And the external network is an interface where the general public can access. So there is a website, and there is also the big data platform to provide data.
나중에 다시 나오면 자세히 설명드리겠습니다.
I'll provide you with more explanation later. And every year we host AI competition. And previously we did not have any systems to organize the AI systems, but this website can be used to organize the AI competition. And there's also an internal network, which is used for forecasting and warning. And this external and internal network is linked so that these 2 different networks can share the same data.
예, 그러면 저희가 이제 클라우드 디지털 기반이라 하면 일단 클라우드가 들어가야겠죠.
So because we wanted to have a digital system, we introduced the cloud. So we have all virtual servers. So we have the physical on-prem server, and we also have the cloud virtual server, and we have VMware and KVM, which is an OpenStack. So the VMware is used for forecasting and warning because it's highly stable, and the KVM environment is used for model integration and for R&D projects. So we've established and introduced these 2 different virtualization environment or virtual environment. We established AI and big data system as well. We have 4 GPU servers and we have 10 big data servers. And there's also NAS storage, which is about 4.1 terabyte. Petabyte. And in order to allow AI-based analysis, we should be able to process a huge amount of data. That's why we set up the InfiniBand EDR, which is 100 gigabytes. Now I'll talk about the development of the business system. Talking about the forecasting and warning system. And this system is developed to have functions that will allow analysis, visualization, and linkage with other business systems. And it recognizes automatically the changes of the weather or the space weather, and it can produce warning messages or warning notification. And the warning text is automatically generated and distributed. So we have standardized the business processes, and through data analysis, we can also automate the forecasting service. We can also automatically recognize the changes of the space weather environment, and we combine or collate different models, and the outcomes of the modeling can be used. Now I'd like to talk about the development of the AI and big data system, and it allows big data analysis, and it can also process huge monitoring data. An AI prediction model has been developed, and we also have established an R&D environment, and we have established the big data platform, and we use the Brightix BDH and for the big data management. And also for big data analytics, we've introduced Brightix machine learning, which is a Hadoop-based SDS. And in order to, when it comes to, this provides a quality environment, and for visualization, we use Tableau. So from the big data portal, data search, provision, utilization, and other communication with users, and history management can be done. So this is the execution screen of the SDS Brightix AI, and this is easy to use, and by drag and drop you can bring data onto the screen, and you analyze the data, and you can set the analytic algorithm conditions, and then you see the analytics outcomes without any coding. And so we have set up this easy-to-use environment, and this is also available externally. And this is a history management system for forecasting.
지금의 태양 환경, 우주전파 환경과 과거에 어떤 환경과 과거에 어느 시점의 환경과 비슷했으면
if there is a similarity in space weather environment in a point of time in the past with the space weather conditions of now, we can derive some insights on what's going to happen. So in order to identify some relevant information from historic data, for example, we can identify the sunspots and flare data, semi data, or filament data, and coronal hole data, and that's used for space weather prediction. And this is the big data portal system. We can inquire and analyze the previous space weather disasters or the RSG warning history, and through this business we can also, and we have developed geomagnetic disturbance prediction. Now, speaking of the disaster response system, before our response was quite manual. So in case of any event, we called the relevant authorities and we exchanged documents using fax and email. But now that we have established this system, a lot of the processes have been automated. So reporting, dissemination of information, drill, and other information visualization can take place automatically utilizing this system. And also it is linked with the National Disaster Management System in order to develop the relevant information real time. So these are screenshots of the response system. So from the moment of the event breakout to end of situation, there are different processes that can be done. And if there is a report to be generated,
다음 프로세서로 넘어가고
The approval process can take place on this system,
정부에서는
and based on the approval,
재난 등급을
the head office can
결정할 수 있는
determine
그런 체계를
the grade of the disaster.
재난 대응 체계들을 그런 시스템을 통해서
So,
갖고
utilizing this system, the disaster response system can be implemented. Now, talking about the integrated control system, in Korea, there are about 200 types of space weather monitoring data, and we can now collect those data on a real-time basis, and we've also developed a database.
잘 관리하기 위해서
In order to better manage this system,
그러니까 관측부터
from observation to data analysis and usage, the entire data flows can be monitored, and in the event of any failure, it could be notified automatically. So not just all the business processes, but all the monitoring stations can be monitored utilizing this integrated control and command system. So this is a screenshot of this system. You see we have different servers for different business tasks, and we also have the observation and monitor system that's also included in this dashboard.
다음 전자식 공유 시스템입니다.
This is the knowledge sharing system.
업무를 하다 보니까
When we conduct our everyday business, sometimes there are issues with shift turnover, and there were times that we were not able to really search historic data or business information. So we put together all the information and data at one place, and we've categorized the different types of information so that internal users can easily search and access those documents whenever and wherever. So data information was collected, and AI-based system was created, and we have the central document repository, and we've extracted the text, and there is an automatic document categorization process, and that really helps the users to pinpoint the document that they require. So it's similar to the Google directory. If you enter your keyword or search word, then you have the detailed conditions that you have to provide to find the document that you are looking for. Now, this is an external system that we've developed. So this is our new website, and it also provides the data analytics project website, and AI and cloud-based system has been created. If you visit our website, the UI has been upgraded, and responsive web technologies have been applied. And this is a big data platform. And domestic overseas monitoring data are collected, and it's made public to the general public. So it's provided in a downloadable format. And we also organize AI competition. And this website hosts the AI competition, so participants can register on this website, and we also can set up an environment within which the participants can develop their own models and evaluate and validate their models, and also we can give different ranks to the participating competitors.
제가 좀 강조해서 말씀드리고 싶은
One thing that I would like to highlight is that this AI environment is free of charge.
일반 분석과 전문 분석이 있습니다.
There is general analysis and professional analysis. For general analysis, you can use Brightex AI, and for professional analysis, the people who are using the website can use Python or R. So Jupyter Notebook will be downloaded, and on that Jupyter Notebook, you can build your model. So this environment is provided for the general public free of charge. So if you've accessed our website, you can do all these things, and unfortunately it's not well known, but it does exist. We have 38 prediction models, at analytics models, and now we put together all those models in one place so that we can have a single model input and output system.
네, 이것으로 발표를 마치겠습니다.
Well, that's the end of my
감사합니다.
presentation. Thank you very much for your attention.
혹시 질문
Are there any
있으시면
questions about my talk?
네, 질문이 없으면
Since there are no questions, let us move on to the next presentation.
네, 이어서
Moving on,
경희대학교 이강호 박사님께서
we'd like to listen to the presentation of Dr. Lee Gang-woo of Gyeonggi University. The title is Solar Flare Prediction Using Deep Learning. Please give a big round of applause. Good afternoon. My name is Lee Gang-woo from Gyeonggi University. I would like to talk about deep learning technology and solar flare forecasting. This is the content. I would like to first introduce the solar flare, artificial intelligence technology, and wrap up my presentation.
태양 플레어입니다.
This is a solar flare.
태양 플레어란
What is a
태양의
solar
거대한
flare?
자기적 에너지가
Solar flare
태양
is
표면에서
a sudden
빛을
flash
폭발하는
on the
현상을
sun
말합니다.
caused by the release of huge
이 태양
magnetic
플레어에
energy.
의해서 발산된 거대한
And through
에너지가
this solar
지구로
flare,
날아오고 또 이
large
거대한
energy
에너지에
will
의하여
be
가속된
directed
입자들
to
또한
the Earth,
지구로 날아오며
and particles will
인공위성에
be also
피해를 주고
directed to
GPS 오류를
the
유발하고
Earth. So
통신
there
불안을
will be
유발하고
disturbance
또
in
배도 활동을 활성화하고 있는
communications,
우주인들과
satellites, and
고고도
the
항공기
astronomers
승무원들이 우주
and
방사능에
the
노출되는 등 관련
flight
산업과 그
attendants will
종사자들의
be
막대한 피해를 줄 수 있기 때문에
damaged. So
태양 플레어를
there
예측하는
might be
일은
huge
매우 중요한
damage
일입니다.
in economy and
이 태양
society.
플레어
So
예측 분야에서
prediction
활용되고
is
있는
very
인공지능에
important.
대하여
So I would like
말씀드리겠습니다.
to tell you what kind of deep learning
첫 번째
technology is
방법은
used to
컨볼루션
predict
뉴럴 네트워크라는
solar
방법입니다.
flare. The
이
first one is
방법은
convolutional neural
기본적으로
network.
이러한 이미지를
Basically,
분석해서
in this
이
CNN,
이미지가
the
어떠한
machine
분류에
analyze
속하는지를
the
예측하는
image
인공지능 방법입니다.
and
저희는
categorize
이러한
them.
인공지능 방법의 작동 기작을 이용하여
By using the
이러한
mechanism of
형태의 태양
convolutional
데이터를
neural
넣었을 때
network,
이러한
we
태양 데이터가
entered the
플레어가
solar
발생할
image data,
데이터인지 아니면
and
플레어가 발생하지 않을
we
데이터인지
wanted to see
분류를 하는
whether
방식으로
the
태양
image
플레어 예측
can
모델을 제작을 하였습니다.
lead up to the solar
저희
flare or
연구소에서
not.
제작한 CNN
In our
기반
lab,
태양 플레어
we
예측 모델을
created the
분류합니다.
CNN-based solar flare prediction model.
태양 데이터가 인공지능
First,
모델에
we have
들어갔을 때
the solar
여러
image data,
컨볼루션 뉴럴 네트워크
and it
블록을
goes
거쳐서
through multiple
모델은
blocks of
최종적으로
the convolutional neural
플레어가 발생할
network,
점수와
and eventually
플레어가
it will
발생하지 않을
give
점수
the
두
scores
점수를
whether
출력하게
the
됩니다.
solar flare
이
will
두 점수 중에
take
높은
place
점수를
or
고르는
not.
쪽을
And
태양
if
플레어
the
예측 결과로
score
사용을
is
하게 됩니다.
high, then we determine that solar flare will
앞서
take
보여드린
place.
플레어 예측 모델의
As
결과입니다.
I mentioned before,
저희 모델은
this is a solar flare
작년에
prediction
사용한
model,
다른 플레어
and you
예측
can see
모델들과
the
비교를 한
results.
후입니다.
And we also
이
compared our
정확도,
model with
타이트
other
스킬
models.
스코어,
And the
애플맨
first
스킬
one is
스코어, 그리고 트루 스킬 스코어라고
accuracy,
태양 플레어 모델
HSS,
평가 쪽에서 사용되는
SS, and TSS.
여러 평가 지표들을
So
이용하여
these are the
비교를 하였을 때
indicators used in
저희가
solar
만든
flare
모델이
prediction.
기존
And based
모델들보다
on that
조금 더
prediction
우수하거나 비슷한
comparison,
성능을
we
보여주는
can
것을
understand that
발표했습니다.
our model has a superior or similar
또한 저희가 앞서
prediction level.
모델이 두 개의 점수를
Also,
출력한다고 말씀을
as I
드렸는데
mentioned before,
이 두
the model
점수를
provides
합이
two
1이 100에
scores,
치환을 하면
and if we combine these two
레이블에
scores,
대한 점수
the
결과를
outcome will be
인공지능
1.
모델이 예측한
Then
플레어 발생 확률로
we
치환을 할 수
can
있게 됩니다.
turn it into
이
the
X축은
probability of
이런
solar
식으로
flare.
치환하여 얻은
So on the
인공지능
horizontal
기반
axis,
플레어
you can
발생
see
확률의
the flare
플레어 발생 확률에 따라서
probability,
블록을 10개로 나눈 것이고
and we
Y축은
categorize
이런
them
식으로
into
분류된
10
데이터들을
groups.
분석했을 때
And on the
실제로 그
vertical
데이터들에서
axis,
플레어가 얼마나
we can
발생하였나
see the real
나타낸 것입니다.
probability whether actual
이러한
flare
히스토그램을 분석을 했을 때
happened or not.
correlation
And by
coefficient가 0.9고
analyzing this,
그리고
we
1차
can
특징을
understand
했을
that
때
correlation
기울기가 1.0
coefficient was
거의 정확도가
0.99 and
99%
p was
98%의 확률로
1.02
인공지능 모델이 플레어 발생
x
확률을
plus
예측했다는 것을 알 수가 있습니다.
0.01.
이러한 결과들을 통하여
Based on this
CNN을
outcome,
이용하면 높은
we can
성능의
understand
플레어
that
발생
using
모델을 만들
CNN,
수 있다고
we can create
말씀드릴 수 있습니다.
the flare prediction model with
저희가
high
말씀드리고 싶은 두
accuracy.
번째 방법은
And the second
비주얼
method
디스플레이입니다.
is a
시각적
visual
설명
explanation.
이러한
So we can
방법을
visually
컴퓨터
explain
과학 쪽에서는
the
어트리뷰션
outcome.
메소드라고 합니다.
And in computer
이
engineering,
어트리뷰션
it
메소드가
is
하는 역할은
called
특정
attribution method.
이미지를 인공지능
A
모델에
specific
넣었을 때
image can be entered
이
into
이미지를
the
보고
artificial
이
intelligence
인공지능이
model,
줄
and based on the
마스티프라고
image,
분류를 하면
the
도대체 이 이미지의
classification
어느
will be
부분을
done,
보고 이렇게 불 마스티프라고 분류를
and
하느냐
it
그것을 시각적으로 보여주는 방법입니다.
sees
첫
the
번째
image
방법은
and
가이드
understand
백
where is the
프로파게이션이라고
dog.
해서
So
어느 픽셀이
first,
중요한지 이렇게 세세하게 보여주는
the guided
방법이고,
back
두
provocation
번째 방법은
will
그라데이션이라고
tell us
해서
what
이
pixel is
이미지에서 어느
important.
영역이 중요한지
And the
이렇게
second
픽셀
one
형식으로
is
보여주는
grad
방법입니다.
cam. It shows the heat map showing the important part of the image.
분류하는데 중요하게
So
여기는
if the pixel is marked in red, we can understand that based on this pixel, the model understood that this is the pixel for the dog, and the blue area can be ignored. And we apply the grad cam, and in this image, this red area was recognized as an important pixel. As you can see on the slide, the important areas are the area where black and white dots are concentrated. So there is a transition from plus to minus. There is a huge magnetic activity here. Based on the analysis, we can understand that based on the visual explanation, the model can predict the solar flare. And for some AR, there are important AR and not less important AR. So if the model can tell the importance of active area in different level, then we can also see the prediction level as well. So the importance was depicted on the horizontal axis, and on the vertical axis, we also indicated the flare occurrence rate. So we have three histograms. From the top, there are C-class flare, M-class flare, and X-class flare. So it is whether it is a strong flare or not, the flare actually took place in the area where model predicted. So based on the active regions, we now have the understanding about the importance of active region. So we also use the sharp parameter. This is the observation outcome of the SDO HMI, and it is the magnetic characteristics of the active region, and there are 6 parameters. So in total, we used 16 sharp parameters, and we compare this with the importance recognized by the model, and in more than 9 parameters, we confirmed that there are correlations. And as for the total current, total unsigned flux, and total flux magnetic density, these 4 parameters showed the highest correlations. And these 4 parameters can be found from other papers such as the Bobra et al., Liu et al., and Lim et al. These parameters were considered important in many other studies. And aside from the grad cam, we also used the guided back provocation. On the left side, you can see the active region, and it has been expanded. And in the middle, you can see the expanded image of the guided back propagation, and we also color-coded it on the right side. As you can see, there is a boulder between the black and white area. These areas are considered as an important area. So in this area, the magnetic field is the area where we can observe polarity inversion from plus to minus. So from the papers such as Manson et al. And Parkonol et al., polarity invergent lines were mentioned, and they also proved that it is related to solar flare. So this visual explanation was applied to solar flare prediction deep learning model, and there are two benefits. Instead of just accepting the outcome of the model prediction, we can see that from which active area this outcome was created. And based on the understanding, instead of just accepting the outcome of the prediction model, now we can use our insight, human insight. Let me give the examples. In the first picture, you can see the successful case of the prediction. As you can see, the model indicated one active region, and we can also see the polarity inversion line and the size. And this active region has high possibility of creating solar flare, so we can accept the outcome of the model prediction. However, on the right side, you can see the prediction on 2013, February 10th. The model provided the prediction, but the important areas are scattered around, and active region is located at the edge of the image. And the model predicted that there will be solar flare based on this active region. However, there are visual distortion. So this is the active region. When you look at this image with your bare eye, the parameter is not that high, and it is scattered around, and the sun is swiveling from the east to the west. So when there is an actual flare, the flare will take place at the back of the sun, so it is not that important for the Earth. Based on this analysis, when we make the forecast, we can give more thoughts, and we can determine where we will accept the prediction outcome or not. So these two are the benefits of the visual explanation. The third one is reinforcement learning. I'm sorry. When there is a certain condition, in reinforcement learning, the model creates the action. And based on the action, there will be a reward. And based on the reward, training will be carried out. And based on the mechanism of this model, we provided the environment of the sun. And there are two actions, whether there will be flare or not. And we can provide a reward. By doing so, we expected that there will be good prediction outcome. So we used reinforcement learning, and this is very good for biased data set analysis. Let me explain the biased data set. This is also called as imbalanced data problem. Simply put, we have a large data set and train the artificial intelligence, and it is optimized for the frequent data, and for the less frequent data, it is not optimized.
앞서 그 C 클래스가 약하고 M
In
클래스가 강하고
In the previous slide, I said that C class is the weaker one and X class is the stronger one. And when we analyze the solar flare in history, we can understand that when there is one X solar flare, then there are 10 times of M class solar flare and 100 times of C class flare. In order to address the imbalanced data problem,
보상을 기반으로 학습을 한다고 말씀을 드렸었는데
as I mentioned, since this model
그리고 흔한 이벤트를 맞췄을
is
때
trained based on the
서로 다른
rewards,
보상을 준다면
we provided different rewards for the prediction for the frequent data and less frequent data.
연구를 진행해 보았습니다. 강화학습 방법에는
In reinforcement learning, there are multiple methods, but we used deep Q learning network and double deep Q learning network.
Q 러닝 네트워크는
As for the deep Q learning
이전에
network,
강화학습 분야에서 많이 연구가 되었던
it has been
Q 러닝이라는
studied.
방법의 인공지능 적용 버전.
So it is the AI version of the Q learning, and this double deep Q learning network is based on the double Q learning method. We use the same method, however, we apply the outcome of this model to train the model and assess the model. And this is the flow of the model. First, we have the data we want to analyze, and we enter the data into the flare prediction model, and based on that, the model will create the score, and there will be random data for the next analysis. So these four elements will form the one set, and we enter these four sets into the replay memory, and lots of data has been stored in the replay memory. We have in total 20,000 memory, and based on the random data, we train the model, and online agent repeatedly copied that into the target agent, and trained model will have high performance and make better prediction, and better data set will be entered into the replay memory. Based on the better data in the replay memory, a higher intensity of training will be carried out. And this is the comparison of the performance. At the top, you can see CNN. So we used CNN only without reinforcement, and at the bottom you can see 3 DQN. When we apply the different reward, scores will be different. So there are 3 indicators such as HSS, TSS, and APSS. Based on these 3 assessment indicators, we can see that reinforcement learning provides higher performance. And now the model can predict the stronger flare as an important flare instead of frequent weak flares. And the last one is the sequence method. We use time series data to predict predict the traffic or language translation, and when we use this time series data, we can predict the time series data of the M-flare X-ray flux. On top of that, when we predict solar flare X-ray flux, it is not provided as a service across the world. So this is a new trial for us to predict the solar flare. And this is the structure of the model. There is an encoder and decoder. We have 2 models, and encoder will make analysis and provide the outcome to the decoder, and the decoder will enter P plus 1 into P plus 2, and P plus 2 will be used as an input for p plus 3. So there will be 30 times of prediction.
모델의 예측을
So this dotted line shows the prediction time, and
보시는 것처럼
the orange one is the prediction and black one is the observation. And as you can see, the prediction
엑스레이 플럭스만
was quite good.
때문에
And we used X-ray flux. So when we have more input, the prediction will be better. So in the initial and first prediction, there is a big difference between the actual observation and prediction. However, when we carried out another prediction after 4 minutes and after 9 minutes, the prediction is quite similar to the actual observation. Once we have all input after peak, when we have the prediction for the decrease, then the prediction was excellent. And as I mentioned before, this is the first trial for us to make a prediction. So there is no comparable data. So we compared our model with other models. Every minute, we calculated the average. So as for the RMS all, we calculated the average for all the time, and we also calculated the RMS peak. And after the peak, we didn't include the data because we wanted to see the peak. So even though the performance of the prediction was quite good after the peak, it was not that useful. And according to our comparison with other models, we understand that our model showed higher performance in RMS peak and RMS all. And based on the flux, we can also analyze other things. As I mentioned before, this is the outcome for each minute. Based on the flux analyzed by the model, we created the graph of dots, and RMS-E was 6.5 minutes, and as for the peak time, RMS-E was 4.8 minutes. So prediction was quite accurate. And this is the actual sample. When there was a flare, right after the flare, the prediction was not that accurate. However, after 1 minute, the prediction is closer to the actual observation, and as time goes, then prediction is almost similar to the actual observation, becoming stable. The benefit of this method is we can try something new in flare prediction. Please look at the dotted area. This is the flare end time by NOAA's flare definition. From the background to peak time, when there is a decrease by half, then it is recognized as end time. According to NOAA, they say that this is the end of the flare. And if we rely on the NOAA's definition, we can turn on the instruments and satellites. However, still there are impacts. In order to overcome this problem, we need to analyze all the profile and allow the user to turn on the instrument based on the data. And this is the conclusion. We used the deep learning to make the prediction about flare, and we were successful. When we use the visual explanation, we can use scientific knowledge and insights of human being instead of just accepting the outcome of the prediction model. And by using deep reinforcement learning, we can create the model that can predict a strong solar flare instead of frequent weak solar flare. And using the X-ray flux profile, we can also make a new type of prediction. That is the end of the presentation.
네, 발표해 주신 이영.
Thank you very much, Dr. Lee.
혹시 질문 예.
Is there any question? Yes.
네, 좋은 발표 감사드립니다.
Thank you very much for the excellent presentation. My name is Jung Jung-gyun. I'm not an expert in solar flare or AI, but based on the size of the AR, now you are predicting the solar flare.
저희 아이디어는
So our idea is, how can I put this? Without any bias, we provide all the data to AI and make AI to make a prediction. For example, in the limb, equator, and polar area, there are different curves. Based on that, the size of the active region can be different. And based on that, is there any possibility that AI misunderstand it? Yes, you made a good point, and there is a possibility. I actually showed this. I showed the wrong prediction in this slide. The prediction was at the edge of the sun, but because it is located at the edge, the model made a wrong prediction. But we provide continued data for 7 days or 14 days so that the model prediction can have higher performance. Now we have that plan. And if we do mapping, still this area cannot be mapped. Of course, we will consider the mapping, but we will consider other methods as well.
예, 좋은 발표 잘 들었습니다.
Thank you very much for the excellent presentation.
여러 가지 학습을 하더라도 학습이
In training,
큰 것이 지금 중요한데.
now we need to understand the strong solar flare that have huge impact to the Earth, and we need to focus on strong flare.
그런 것들을 통계적으로 의미 있게 뭐 DQN을 써가지고.
You use the DQN for reinforcement,
몇 개 정도 이벤트
but still,
있어야지 이게 충분히 학습이 될 수가 있는지 데이터.
I would like to understand how many data is required to train the machine.
이벤트 숫자가 다른 것이 몇 개 정도.
So how many data did you use?
다른 두 번째 질문은.
And my second question is,
너무 많지 않아가지고.
if the data is not big enough,
자기 스스로 한 학습
then
그런 걸 하지 않고 데이터 기반으로.
instead of doing the repeated learning, for example, if we provide input in WSA model, there is an output and it can be entered into NNIL, and there will be also simulation.
그런 인과관계를 모델을 통해서 데이터를 자료처럼 뽑아낸 다음에.
So after creating a processed data through model, and if we enter that into the model, for the X-class flare, I believe it will improve the performance. So do you have any idea? Thank you very much for the suggestion. Let me address the first question first. You asked about the number of the data. We have that in the slide, backup slide.
아마 이게 태양 23주기를 전부 다.
We used the cycle 23. We used all data available for cycle 23 for the test.
잠시만요.
Wait a minute, please.
제가 그 분류 제가 클래스 분류까지는 담아놓지 않은 것
As
같은데
for the classification, I didn't include that in my slide, but
데이터 수와 플레어가 발생하지 않은 수가 약 반반이었고
the ratio of the flare and non-flare data was half and half.
아마 이 전체 데이터 중에
And as I mentioned before, the ratio was 1
0.5%
to
정도라고
10 to 100. So
안될 정도밖에 없는 것 같아요.
there were only 20 X-class flare data. And as you mentioned, it was very difficult for us because the number of the data for X-class was small.
적어도 어느 정도 맞출 수 있지 않을까 막연하게 기대를
So we blindly expected that the model will make good prediction. Please look at here.
보면 굉장히 선형적인 모습이 안 보여요. 굉장히
In
이상하게
X-class, it is
나오거든요.
not
이거
lineal.
X-클래스만 따로 떼어서 하려면
So if we separate X-class, there should be lots of discussion and preparation.
질문해 주신 두 번째가
And the second question you asked is using different model, different simulation to train the artificial intelligence model. And in AI, the most important part is the scientific fidelity of the data.
그럴싸한 걸 보여주는 게 그 인공지능의 기본적인
Because AI usually shows
그럴싸한 데이터를 넣어서
look good
그럴싸한
data
결과가
instead of the
보여주려고
accurate data.
저희가 논문 출판 같은 거 할 때 그
So if the data is not accurate,
부저함을 보입니다.
then there will be lots of questions when we publish the paper.
과학적으로 중요한
So
데이터
we
기반으로
wanted to
나오는
use
결과에
scientifically important data.
하려고 하고요. 그리고 두 번째로는
Second,
그럴싸한 데이터는 결국 어느 정도의 에러를 띠게 되는데
there might be some errors in not accurate data. So eventually the errors will be amplified.
성능이 좋아지는 데이터 수가 늘어나니까 좋아지기도 하겠지만
With more data, the model itself can be improved. However, due to the error prediction, accuracy will be lower. So we need to test this.
네.
Thank you.
저도 한 가지
I have
질문이
one more question for you.
저희가 예보를 하는 입장에서는
As a forecaster,
오늘 지금 당장 예보를 우리가 3일 후까지를 봐야 되거든요.
we need to forecast next 3 days.
어디까지 지금 뭐
So the window of the forecasting is important.
모델들이 어디까지 며칠까지 예보를
I would like to know what is the window of prediction for this model.
사실은 근데 시간이 지날수록 정확도는 떨어지잖아요.
Over time, the accuracy will be lowered.
뭔가 예측값을
So statistically significant prediction is important. So what is the window?
일단 대부분의 플레이어 예측 경우는 일단 24시간 예측을 기반으로 진행이 되고
At the moment, we are making prediction for the next 24 hours. But in order to extend the window to 3 days, we first need to analyze the data and we need to understand what is acceptable or not. In order to do 3-day prediction, we need to have higher TSS. One of the realistic way to do that is creating the image for day 1, day 2, and day 3. And on day 3, we can use the data to make a prediction. Then we'll make more accurate prediction instead of using the current data and make a prediction for the next 3 days.
다시 한번 큰 박수로.
Thank you very much, and please give a big hand to the presenter.
네, 그럼 이곳으로 모든 발표를 마치고
Well,
세션 3를
this wraps
마무리하도록
up session 3. I'd like to thank the speakers and participants for their kind contribution to this session.
부탁드리겠습니다.
Thank you very much.
자, 이렇게 세 번째 세션을 마무리하겠는데요.
Well, that concludes session number 3. Thank you, the moderator, and I'd like to also thank the speakers.
다시 한번 감사의 말씀을 드립니다.
Thank you so
또
much.
이제 세션 4를 시작하기 앞서서
Before we begin session number 4, we will take a short break for about 20 minutes, and the next session will resume at 2:35. Thank you.